Hello, everyone. This is Chen, and I'm from Shenzhen Institute of Advanced Technology, Chinese Academy of Sciences. I'm sorry that I could not make it on site because of the visa problem. It is my honor to present my work, which is named Swift Fast Performance Tuning with GAN-Generated Configurations. This is completed in collaboration with Shixin Huang, Professor Xuehai Qian, and Professor Zhibin Yu. Nowadays, big data processing has been widely used, and various frameworks are required to process data easily and efficiently, such as Hadoop, Spark, Flink framework, etc. Among them, the configurations of these frameworks play a vital role in system performance. It is worth mentioning that, according to research, the performance can be improved by 89 times through parameter tuning. Below are examples of Spark and Flink configuration parameters. For instance, in Spark, one can specify the executor memory and the number of cores in the parameter so that they can efficiently manage task processing and system resources. There are various parameter tuning methods, where rule and analytical tuning methods leverage the experiences of human experts. Analytical models can be used for precise evaluation and parameter tuning. However, they fail for complex systems. Simulation-based tuning approaches prove system internals and help parameter tuning using simulations. But it is hard to cover all factors in simulations. Machine learning-based tuning methods build a ML performance model for evaluation. A large quantity of samples are used to build ML models, which help tune the configurations. At present, ML methods have become popular for complicated parameter tuning due to their effectiveness. However, conventional ML methods need a large amount of samples to construct accurate ML models. The sample collection is extremely time-consuming because it needs to wait for each sample to finish its running from the execution beginning to its end. For example, from the table on the left, we can see that for some Spark program benchmarks, it takes many hours for the sample collection process. To speed up the ML methods, Bayesian optimization has been proposed. Nonetheless, as the data size increases, Bayesian optimization is still slow. From the right figure, we can observe that it can take more than a week to finish the Bayesian optimization parameter tuning on 1 terabyte of data. In the parameter tuning process, we regard the configuration as a vector. C1, C2, Cn, these are its elements, etc. To generate a high-quality configuration, the goal is to ensure that the target and generating configurations are similar but not too similar. Similar is to ensure generated configurations are similar to real applications. Not too similar is to allow exploration. If the target is a good configuration, it guarantees that the next sample selection starts from a good sample. We use the generative adversarial network, GAN, for configuration generation. because the GAN is well known to generate data that have the distribution similar to the input data. We measure the configuration similarity to evaluate the generation quality. The first intuitive measurement method is one neighborhood method. Essentially, one neighborhood uses the Manhattan distance to capture the similarity between configuration vectors. The equation is as follows. It generates configurations according to a target configuration based on small random perturbations. Note that one neighborhood only measures vector distances, and configuration distributions are not used for generation. We then come up with another metric for measurement. That is Jensen-Shannon divergence, and we use it as the ideal metric for measurement. On the one hand, Jensen-Shannon divergence is widely used for quantifying two probability distribution similarities. On the other hand, it happens to be inherently used by GAN as a loss function to ensure resemblance of input images. Although our work focuses on one-dimensional configuration vectors rather than images, we adapted this principle to our domain, where training GANs is simple as well as fast. Therefore, we have proposed Swift. The key idea is to utilize GAN and Jensen-Shannon divergence to generate configurations, which ensures not only short distances of vectors, but also similar distributions of element values. The figure A shows that all GAN-generated configurations have performance close to that of the real configurations. The figure B illustrates the distribution of Jensen-Shannon generated configurations. It's much closer to the real configuration than one neighborhood generated ones. This figure shows the conceptual demonstration of performance in three methods. That is, conventional Bayesian optimization, one neighborhood plus random generation, and Swift. Swift mixes random and GAN-generated configurations that have similar distributions with the current best performance configuration. From figure C, we can see that conventional Bayesian optimization finds optimal configuration with longer time. It fluctuates because of random configuration generations. One neighborhood plus random method goes stuck at the local optimal. Swift outperforms conventional Bayesian optimization and one neighborhood plus random methods, and it finds optimal configuration with shorter time. This is the design overview of the whole system, which is not trivial. The whole system is composed of 4 components. Each component is explained in detail in following slides. The first component is the configuration generator. Swift requires 2 configuration generators. A random configuration generator, RCG, and a GAN-based configuration generator, GCG. The RCG sets each configuration parameter to a uniformly random value. The GCG utilizes GAN's nature to mimic the data distribution of the element values of target configuration and generate configurations accordingly. The configuration profiler component executes a program with a configuration and records its performance, generating a sample SPV equal to PF and the configuration vector. After profiling a program a number of times, all the vectors form a matrix that represents the evaluation set as shown in the figure. The Gaussian Process Builder component leverages the configuration profiler to generate vectors and use these samples to calculate the initial performance mean and the covariance between the performance and the configuration. For the kernel, we choose Martin 5.2 as it does not require strong smoothness and is preferred to model practical functions. The last component is the configuration arbiter. Essentially, it checks if the generated configuration of the best potential performance is in the evaluation set. If it is a new configuration, it is added to the evaluation set. This way, the evaluation set contains the best configuration as the iteration continues. To evaluate the effectiveness of Swift, we employ 8 servers as follows. Each server is equipped with Intel Xeon processor and 64 gigabytes of memory. We use Ubuntu as the operating system and test Flink and Spark big data analytics frameworks. We use a HiBench suite for batch and stream benchmarking. We first evaluate the quality of the generated configurations. We compare 1 real and 3 GAN-generated configurations in a caveat plot. There are over 20 configuration parameters in this plot, such as TN, MF, BFRT, etc. The values of each parameter is normalized between 0 and 1. We can see that it is clear the 3 generated configurations are very similar to the real configuration. We also evaluate the hyperparameters of the system using the repartition program. The top figure is the speedup with different number of initial configurations. We can see that when 5 initial configurations are used, the speedup is the highest. The bottom figure is the performance variation with different threshold values. We find that the ideal threshold value is 3. Then we use Flink stream benchmarks and compare Swift with cherry pick, select DAC and GML. From the table, we observe that the optimization times of the other methods are 2.2, 4.3, 9, and 7.2 times that of Swift. That is to say, Swift tunes the parameters much faster than other methods. The two figures are the latency and the throughput of different methods. On average, Swift exhibits 1.28 times improvement. Therefore, we conclude that Swift possesses better performance with shorter time for Flink benchmarks. Similarly, we evaluate Spark batch processing benchmarks using different methods. Comparisons indicate that the optimization times of the other methods are 2.2, 1.2, and 1.4 times that of Swift. Overall, Swift exhibits better performance with shorter time for Spark benchmarks as well. In this figure, we take word count benchmark for evaluation. It shows that Swift mixes randomly and GAN-generated configurations and has the effect of skewing the search space toward the optimal configuration, leading to faster convergence. cherry-pick, performs uniform space search, and experiences fluctuations throughout the process. We perform a detailed case study on the fixed window benchmark. We see that, compared to default configurations, Swift achieves a speed up by 10.7 times. Specifically, the CPU utilization increases by 7.5%, and the memory utilization reduces from 64% to 20%. That is to say, we achieve the system performance improvement by busier CPUs with reduced memory accesses. We further investigate how the parameters affect the performance. We quantify the importance of configuration parameters for fixed window with respect to its performance. TRHB, CDRI, and CDAL are the three parameters that improve the system performance with the most correlation. Their meanings are as follows. We observe that they are all related to memory. For example, TRHB is the task manager runtime hash join Bloom filters. It specifies whether we should enable Bloom filter for the hybrid hash join operations. The Bloom filter is a bit vector that is essentially a probabilistic data structure. It tells us that the element is either definitely not in a set or maybe in a set. The Bloom filter can be enabled and help reduce the memory consumption and increases the CPU utilization. In conclusion, conventional Bayesian optimization is slow for configuration optimization, with configuration search fluctuations. We leverage the GAN network and the novel Jason-Shannon divergence mechanism to address the challenges of fast configuration tuning. Compared to the state-of-the-art methods, Swift provides better performance with shorter time for both Spark and Flink data analytics programs, which is demonstrated by the experimental results. Thanks a lot for your attention.